Lewis structures, also known as Lewis dot structures, are a means for us to take a look at the structure of molecules using their valence electrons. The primary purpose of Lewis structures or Lewis dot diagrams is to show the structure and the use of the valence electrons from the bonding atoms in a molecule. This video clip will be specific to our third unit of study, objective number 1, which is be able to draw a Lewis structure for a molecule or polyatomic ion. As we start this video, have 3 things as we prepare to go through the video. Some paper and pen to take notes, a copy of the Lewis structures guidelines, and a copy of a periodic table. The first step in our Lewis structure guidelines is we have to count the valence electrons for all the atoms that are in the particular compound we're working with. When we consider the valence electrons in an atom, the valence electrons are the outermost, or specifically, valence electrons are the electrons of highest N value in the structure of an atom. For example, in carbon, the highest N value is 2. We have 2 s electrons, also 2 p electrons. Carbon has 4 valence electrons. Say we have an element such as iodine. Iodine's highest N value electrons are the 5s2, 5p5, so we would say that iodine possesses 7 valence electrons, and that we only count the electrons that are located in the highest N value. Those are our valence electrons. In our atoms, the valence electrons, those of highest N value, will always be those that are just the s and p electrons in our valence structure. The periodic table can be used to count our valence electrons by counting the location in either the s or p subblock. For example, for iodine, we're only counting electrons of highest N value, which is essentially the s and p's. We have 1, 2, 3, 4, 5, 6, 7. Since we've moved 7 columns in the s and p subblock, that identifies that iodine has 7 valence electrons. Let's try our first compound, phosphorus trichloride. Find the column that phosphorus is in. The column indicates phosphorus is going to have 5 valence electrons. Chlorine is 2 columns over. Each chlorine atom will have 7 valence electrons. We have 5 valence electrons for phosphorus. Because there's 3 chlorine atoms in our structure, we're going to multiply the number of electrons in chlorine times 3. This gives our compound of phosphorus trichloride 26 total valence electrons. Check, we're done with our first step in the Lewis structure guidelines. Our next step is to do what's called draw a skeleton structure of our compound. Skeleton structure is taking the first atom, make that the central atom, and then draw a single line to each of the other atoms in the structure to connect each atom to the central atom in our Lewis structure. This would be what we'd call our skeleton structure for PCl3. We're now done with step 2. Check. Our next step in the strategy is to find out how many electrons, valence electrons, are what we refer to as still available to complete our valence structure. Each line that we've drawn represents a covalent bond, a single covalent bond. A single covalent bond is where the electron cloud of phosphorus is overlapping with the electron cloud of chlorine, and a pair of electrons is being shared between the 2 atoms. That creates what we call a covalent bond. Each single bond counts for 2 electrons that are already being used in our Lewis structure. These electrons are no longer available to be used for other aspects in completing the Lewis structure. Our PCl3 has 6 electrons that are being utilized in bonds currently in our structure. We do is we subtract the 6 electrons in bonds. We take that away from the total of 26 valence electrons that we determined we have available for our structure from the atoms PCl3. And this leaves us with 20 electrons that are still available to complete our Lewis structure. That completes step 3 for us. Step 4 is now we want to determine the number of electrons needed to complete what's called the octet for each atom in our structure. One of the driving forces in bonding is that atoms are trying to achieve what's called an octet, or reach a state where they have 8 valence electrons. This is one of the reasons molecules get formed from atoms. An octet is a desirable electron arrangement because it mirrors the arrangement of electrons that we see in a very stable arrangement when an entire outer or highest n levels electrons are filled, as we see in a noble gas electron configuration. So each atom on our structure desires to have 8 electrons, or an octet of electrons around that atom. Each bond counts as 2 electrons. If we initially focus on the phosphorus atom, phosphorus already has 6 electrons surrounding it, 2 electrons in each of the bonds attached to the phosphorus. So phosphorus still needs 2 electrons to complete its octet. Focusing on a chlorine atom, the bond counts for 2 electrons, so this chlorine needs 6 more electrons to complete an octet and have a total of 8 valence electrons. The other chlorine atoms also need 6 electrons each, so we have 6, 6, 6, and 2. That adds up to 20 valence electrons are needed to complete our Lewis structure and provide each atom with an octet of electrons. Our next step is we want to compare what we just determined, the number of electrons needed, compare that to the valence electrons still available determined in step number 3. Comparing, we see that our number of electrons needed, 20, is equal to the number of electrons we still have available to complete our Lewis structure. In this scenario now, where the number of electrons available equals the number of electrons needed, the next course of action is we distribute the electrons to fill the octets for each of the atoms in our Lewis structure. Take our 20 electrons available, add a pair of electrons to phosphorus, add 3 pairs of electrons to each chlorine atom, and we've distributed our electrons such that we've now completed the octet for each one of the atoms in our structure. By distributing 2 electrons to our phosphorus and 6 electrons to each one of our chlorine atoms, each atom now has an octet, and we've used up all of our electrons that we had available to complete our Lewis structure. Last step is to recheck our Lewis structure. Earlier we added up that we had 26 total valence electrons from phosphorus and 3 chlorines. Checking our structure, we should not have more than 26 valence electrons in the structure. You see, we have, counting up all of our pairs of electrons, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and here's 26 electrons. That matches our total valence electrons. And we can also see that each of our atoms has got its octet of electrons, which is the driving force behind why atoms form molecules. They want to get that stable arrangement of having 8 valence electrons around the atom. Let's do another example with the NO2 1- polyatomic ion. You can find nitrogen and oxygen on the periodic table. The periodic table will tell us that nitrogen has 5 valence electrons, oxygen has 6 valence electrons. Determining our total, we have the 5 for nitrogen plus 2 times 6 for our 2 oxygen atoms, and then we add on 1 extra electron. Since our polyatomic ion has a 1 negative charge, that means 1 extra electron has been added on to this structure to give it that negative 1 charge. Adding up, we find for NO2 1- we have 18 total valence electrons for our structure. In our skeleton structure, the first atom, nitrogen, is the central atom. Then we draw a single line representing a single bond connecting each oxygen to the central atom. This would be our skeleton structure for NO2 1-. Our next step is to determine electrons still available to complete the Lewis structure. Each bond counts as 2 electrons that are no longer available to be used in completing the Lewis structure. We subtract out the 4 electrons that are being used in bonds from our initial total of 18 valence electrons to give us 14 valence electrons that are still available to complete our Lewis structure. Next step is determine how many electrons are needed to complete the octet for each atom. Nitrogen already has 4 electrons from 2 electrons in the bonds, so nitrogen needs 4 more electrons to complete its octet. Our oxygen atom in the structure has 2 electrons counting for it in a bond, so this oxygen needs 6 more electrons to complete its octet. Adding up, we have 6 electrons needed for one oxygen, 4 for nitrogen, 6 for the other oxygen. Which means we have 16 total electrons that are needed to complete this Lewis structure. Our next step is to compare how many electrons are needed, 16, with how many electrons are still available to complete our Lewis structure. In this case, we see the number needed is greater than the number we still have available. When the number needed comes out to be greater than the number available, we have to now make double or triple bonds in our Lewis structure. For each 2 electrons of difference between the electrons needed and the electrons available, when the electrons needed is greater than the amount available, for each 2 electrons we add 1 additional bond to our Lewis structure. In this case, because 16 is 2 electrons greater than the amount available, 14, we're going to add in 1 additional bond to our current Lewis structure. So we add 1 extra bond to our structure, giving a double bond between one of the O's and the N. We now recheck how does our number needed and available compare. We now have to subtract out 6 bonding electrons because we have a double bond which has 4 electrons, 2 electrons here. We had 18 electrons originally for our structure, 18 valence electrons available. We subtract the 6 electrons now in bonds in our structure after we've added in our double bond that we have, which leaves us now with the new skeleton structure, 12 electrons available to complete our Lewis structure. We have to redetermine how many electrons are needed for each atom to complete its octet. Nitrogen, with a double bond on one side, a single on the other, has 6 electrons in bond, so nitrogen needs 2 electrons to complete its octet. Our oxygen on the right has 2 electrons in a bond, so this oxygen needs 6 electrons to complete its octet. The oxygen on the left has 4 electrons in the double bond, so this oxygen needs 4 more electrons to complete its octet. We now find for this skeleton structure we have 12 electrons that we need to complete the octet for all of our atoms, and 12 electrons are still available. So they are now equal to each other when we compare them. Our next step is when the electrons needed and available are equal, we distribute the electrons remaining to complete the octet for each atom in our structure. So we add a pair to our nitrogen atom, which gives nitrogen now 8 valence electrons. We add 3 pairs of electrons to our oxygen on the right, which completes that oxygen atom's octet. And we add 2 pairs of electrons to the oxygen on the left, which fulfills that oxygen's octet. This would now be our Lewis structure for the NO2 1- polyatomic ion. Charged structures have one more step. We add a bracket around the structure and write a 1- on the outside to indicate that this entire structure has a -1 charge, meaning it has 1 more electron than the total number of protons present in the structure. Let's do one more example structure, astatine trifluoride. Our first step, we see that both fluorine and astatine are in column 7, indicating these have 7 valence electrons for each atom. Adding up our total electrons for astatine trifluoride, we find that we have 28 total valence electrons for this molecule. Our next step is draw our skeleton structure, placing astatine, the first atom in our formula, at the center. This would be our skeleton structure for astatine trifluoride. The next step is determine how many electrons are still available to complete the Lewis structure. We have 2 electrons in each of our single bonds in the skeleton structure. Subtract out the 6 electrons in bonds from our 28 total valence electrons. leaving us with 22 electrons still available to complete our structure. Astatine already has 3 bonds surrounding it. The astatine needs 2 more electrons to complete its octet. Each fluorine atom has a single bond, which counts for 2 electrons, so each fluorine will need 6 electrons to complete its octet. Adding up all our electrons needed, we see we have 20 electrons needed to complete the octets for our Lewis structure with each of our atoms. Comparing the number of electrons needed, which is 20, with the 22 electrons we had still available, we can see the number needed in this circumstance is less than the number of electrons still available to complete our structure. In this circumstance, when the number of electrons needed is less than the amount we still have available, the strategy is we add the extra electrons to the central atom and end up violating the octet rule. So in this circumstance, when the number of electrons needed is smaller than what we have available, the excess electrons get added on to the central atom after we distribute our electrons. What this does is have the central atom violate the octet rule. So each fluorine atom is given 3 pairs of electrons to fill the octet for each fluorine atom in our structure. We'll give astatine 1 pair of electrons to fill its octet. At this point, we still have 2 electrons from our available electrons remaining. The extra 2 electrons get attached to the central atom, and the central atom now is an octet violator, which is possible for the central atom to violate the octet when the valence electrons of the central atom are at n equals 3, energy level 3 or higher. And this would be our final Lewis structure for our astatine